Okay, Algebra 2 class, this is the rest of the notes for 8.1.8.2 Part 2, Applications of Exponential Functions. So let's do the example for the problem or the formula we were looking at, which is interest compounded k times per year. So remember that k is the number of times per year that the interest is being compounded. And I've posted a couple of videos that might explain this a little bit more, but basically you're earning more interest in the year the more times it's being compounded in a year. So more compounding is good. Okay, so we're going to do example 3 in your notes. Okay, and we're only going to start with A because B requires a separate formula. Okay, all right, so let me zoom in a little bit. So the formula that we were using, A equals P times 1 plus R over K to the KT, we need to identify some of those things. So remember what each of those things stood for. P is the principal amount, the initial amount. R is your interest rate as a decimal. K is the number of times per year, and T is your years. A is the amount of money in the account after T years, which we didn't write on there, but we can add that here. So A, which is this one, equals the amount, so money, in the account after T years. Okay? All right, so let's take a look at this problem. So it says, suppose you invest $5,000 at an annual interest rate of 6.9% compounded monthly. How much will you have in the account after 10 years? So, first of all, the $5,000, that's what we're investing. That is your principal. Next, the interest rate of 6.9%. That's your R, but we need to change it to a decimal. Not a percent. So you can either divide that by 100 or move the decimal to the left twice. And so as a pure decimal, that's 0.069. And then the other piece of information we need is K, which is the number of times in the year that we are compounding the interest. So that it says monthly. So that means that K equals 12. Okay, so putting this all together, our formula would be A equals 5,000 times 1 plus 0.069 divided by 12 to the 12 times T. And in our problem here, our T is 10 years. So I'm going to plug in the 10 from the 10 years here. Okay, so at this point you're going to need to get a scientific calculator. Google to the rescue! Okay, so, uh-oh, I already forgot what my numbers were. Let's scoot over here. Okay, here we go. So this was what we were doing right here. So you're going to want to start in the parentheses. Specifically, you're going to want to start right here. Okay, the order of operations is going to be super key here. I'm going to start by dividing these numbers. Then I'm going to add 1 to it. So then I have all of this stuff in the parentheses. Okay, now this 12 times 10 is 120. I don't need to do that math in the calculator. So I'm going to do this in the calculator and then take it to the 120th power. And then finally multiply by 5,000. Okay, so let's do this. All right, 0.069 times 12. Divide by 12. I'm already messing up. Clear, clear, clear. Okay, it gives you that. Then we're going to add the 1 to it. Easy. And now we're going to take it to the 120th power. So x to the y. Alrighty. Woo, okay. It doesn't get much bigger. than it was before. It was 1.00575. We take it to the 120th power, it doesn't really change that much. Whoa, where'd you go? There we go. Okay. And that's because the number itself, 1.0057, is so close to 1. Taking it to the 120th power is like almost taking 1 to the 120th power. 1 to the 120th power wouldn't change at all. So if it's something just a tiny bit bigger than 1, it's going to be really slow to change very quickly. Okay, so at this point, all I have to do left is multiply by the 5,000 here. I have this number. Okay, times 5. Oh, not 50,000, $5,000. Okay, I mean we eventually got a number that was very close to 2, 1.98977. So that's almost 2. And when you multiply 5,000 by 2, you get almost 10,000, or you get 10,000, right? So we got something almost 10,000. So we almost doubled our money in 10 years. It's just not bad. Okay, so $9,948 and say 90 cents. Okay, so this part B has to do with the other formula that we had here. So let's look on the other side. Okay, there's another formula. It's called interest compounding continuously. Okay, so I'm going to try to give you an overview of what the formula is. So imagine the interest rate is a 1 for simplicity's sake. Okay, and pretend that the t isn't there. And don't worry about the p. Okay, so let's just say we have this in 1 plus 1 over k to the k power. So it's similar to what you have here. I'm just reducing it a bit. So compounding continuously means over and over and over and over and over, almost in an uncountable way. So think infinity. Okay. So I'm gonna go ahead and plug into this different values of k, and I'm gonna write the result here. So if we plug in, we'll say 1 for k. And so that would be 1 plus 1 over 1 to the 1 power. That gives you 1 plus 1, which is 2, to the first power is 2. Okay, that's not that hard to calculate on off the top of my head. But I'm going to make them bigger. Let's do 10. So that is 1 plus 1 over 10 to the 10th power. So for this you would need a calculator. Okay, so let's calculate that out. Let's clear all this. 1 plus 1 divided by 10, 1.1, to the 10th power. Okay, that's 2.59 about, approximately. So if you keep doing this, let's do 100. My goal is to get to infinity, which is not really possible, but we're just going to get really, really big. Okay, so let's do 100. So same idea. 1 plus 1 divided by 100 is that. Take that to the 100th power. You get 2.705. Okay, and we're going to do it again. So 1,000. So 2, or clear, wrong. 1, I'm not even going to write the whole thing out. It's 1 plus 1 divided by 1,000. Take that to the 1,000th power. Okay, you get 2.718, about 17. Okay. If you keep doing this, if you put in 10,000, if you go 100,000, you're going to approach a number called E. All right. So E is like pi in that it's a constant, it's a number. There's a couple videos on your checklist that I want you to watch about E. Watch those videos so that you can determine some information about E. Okay, but there's a little button on your calculator that's E. If you push it, that's E. 2.71828182846 blah blah blah. It's an irrational number, so it's going to go on forever and with no repeating decimals, just like pi. But it's a really important number in many fields, specifically finance. And so I want you to watch those videos. They're really short, like 5 minutes max, and just to kind of get some ideas about what E is, okay? And then I want you to go ahead and add what E is to your notes in this little cloud bubble. So E, I told you what the number is, and we can just approximate it to 2.718. 28 dot dot dot. Okay, so there's more about E. I want you to watch those videos. Okay, so why do we care about E here? Because when we do this problem, this formula up here, and we do interest continuously, all of this kind of turns into E. Okay, specifically we get a new formula. A equals P, which is the principal, times E, the number E, to the RT power. Okay, the R does move around, but we don't need to worry about how that happens. It's complicated. Okay, so the E is this number. It's a number. Then we have the P, which is your principal, so same as before. The R, which is your interest rate, the same as before, and T is yours, same as before. So now let's go back to this problem. It says, determine how much more you would have if the interest were compounded continuously. So we're going to redo this problem and then compare how much more money we would have if the interest was continuous instead of monthly. So we were replacing the monthly with continuously. So that's almost like infinity, right? Okay, so we are going to use the same. So it's P-E-R-T, which sometimes I refer to as PERT. P is your principal, so 5,000. E is the number E. R is your interest rate, which is 0.069, times T, which is our time, which is 10 years. Okay, it's actually a little simpler than the other one. So, all right, so let's get the calculator out and let's figure out what this is. So first thing I'm gonna do is calculate the 0.069 times 10, which is really just moving the decimal place over since we're multiplying by 10, right? 0.069 times 10 is actually 0.69. It just moves the decimal place over. So now I'm going to take E to that number. Okay. And so there's E. So I'm going to take E to 0.69 power. It gives me that. And then I'm going to multiply that times the 5,000. Okay. You're not going to notice a huge change here, but there is a difference. So it's 9,968 and 58 cents. Okay, so we can subtract these two, and it looks like we're going to make an extra like 20 bucks. Yeah. 20 bucks for doing nothing though. That's not bad. Okay. Last type of problem, half-life of a radioactive element. So half-life is a type of decay, radioactive decay. So if we think of decay, we have an amount and it's decreasing and it's decreasing and it's never actually going to get to nothing. We're talking about cutting something in half. Okay, so the decay factor is a half. Everything is getting cut in half. So if we have like 50 grams here, then the next time we're going to have 25, and then half of 25, 12.5. So it's cutting in half each time. Okay. And when you take something tiny and cut it in half, you still have something, right? And you keep cutting something in half over and over and over and over. It's never technically going to go away. It's going to get really, really tiny. Okay. So generally, this is the formula that, it's not really a formula. I'm kind of making up this formula. You have your initial amount, A, and since it's a half-life, we're cutting things in half. So the base here is 1/2. But the half-life is a time that it takes to be cut in half. So a half-life is a time it takes to cut in half, for the amount to cut in half. And so you're not just going to put t here, you're going to put t divided by the half-life, whatever that period of time is. It could be days, years, hours, minutes, it depends. Okay? All right, so again, the A is just like before, it's your initial amount. That's what you're starting with. And then the half-life is this, the time it takes to cut in half. Okay, so here's our problem. I-123 is used in thyroid scans. It has a half-life of 13.2 hours. Write the exponential decay function for a 45 milligram sample, and then find the amount remaining after 5 hours. So our initial amount is a 45 milligram sample. Our half-life is a 13.2 hours. That color is awful. Let's use blue. Okay, so there's your half-life. All right, so plugging in our formula, y equals 45 times 1/2 to the t over 13.2 hours. Okay, so if we want to figure out how much is left after 5 hours, we're going to plug in 5 for t and calculate it. Okay, so I'm going to start with the exponent. 5, actually we could use, it might be useful to use parentheses here. Okay, there are parentheses here. So I'm going to start with the 1/2, or you can write 0.5. So it just tells me 0.5. 0.5 to the power of, and I'm going to use some parentheses, 5 divided by 13.2, close parentheses. And then I'm going to multiply by 45. Okay, so after 5 hours, it's not cut in half yet because it hasn't been 13.2 hours. It's less than that. So you're still going to have more than half. And it looks like we have 34.6 milligrams. Okay? All right, this video is done.